Good morning. So today we are going to move. So we talked about Bayesian posteriors for estimation in the first week to obtain rates of convergence of posterior distributions. So that's the estimation aspect. The last two lectures we focused on getting uncertainty quantification, so building confidence sets from Bayesian credible sets for square root of n, 1 over square root n estimable functionals. And there is a last aspect of the trilogy of statistical inference we didn't talk about much yet, is testing. So today we'll talk about testing. And but before that, let me be a little bit more precise just about the end yesterday. So we proved the Bayesian-Donsker theorem. And I said so that we could get some confidence band from it. Okay, so let's see how in practice we can do that. Okay, so the picture is like this. So suppose we recall that we're interested in the problem of getting a confidence band, say for capital F, the distribution function for simplicity. Okay, so you have a picture like this. So here maybe F. So F we don't know, but suppose this is, for instance, the centering. Okay, centering, which I call Tn. Okay, and suppose here I have some draws from, so in yellow I have a draw from the posterior of f dot given the data, so that I know using some sampling method like MCMC, I will know how to draw from it. Okay, and what we'd like to do is to build a band here, so maybe something like this. Okay, here we're on 0, 1. Okay, so one simple thing that you can do is that you can just define n of x as a quantile for the sup norm. So pi of the set of distribution functions such that square root n f minus my centering Tn in the sup norm is smaller than Rn of x. Okay, given the data, I said that this is equal to 1 minus alpha. Okay, so when I solve for this equation, that I can do in practice. Okay, I can just, from my samples f, I can estimate this Rn of x. Okay, if I draw capital N samples in yellow here, I can see here I'm just looking at a quantile of the rescaled sup norm, okay, in the posterior for capital F. So that I can estimate, you know, I draw many capital N times from my posterior here on F given X, and I will have a quite precise estimate of this quantity, okay? And it's a consequence of, so the Bayesian-Donsker theorem so I didn't talk much yesterday about the centering. I told you that I was leaving a bit this aspect aside, but it needs to be, so when we talk about BVM in general, we want that the centering is efficient, so you have to check that. So you can take different things. Either you prove that the posterior mean is an efficient centering, so f bar n, the posterior mean on capital F, or you can take also something like the empirical distribution, but truncated. You have to truncate it. So if you want the, okay, so we have this primitive map here, L, and we can apply it to some truncated version of the empirical distribution. So we cannot take the empirical distribution because we can check it wouldn't belong to the space M, but we can truncate at some index Ln. So that's a bit technical, so I don't really give details about this, but it is possible to show that you have an efficient centering. Okay, so that shows that, so if we set Cn to be this set, then by essentially the same proof as the proof that just quantile credible intervals are in fact confidence interval asymptotically, so that implies that Cn of x verifies the following. So P F naught, that capital F naught belongs to Cn of x. This will go to 1 minus alpha as n goes to infinity. Okay? So therefore, this confidence band, this is really a confidence band asymptotically. Okay? And the proof, so I'll not give it here, but it's really the same as for the intervals, except that it's a bit more technical because so you need to invoke that, so the distribution function of the Brownian bridge is continuous and strictly increasing. That's not very hard to prove. And also you have to prove that the distribution functions, when you have convergence in distribution to the Brownian bridge, the distribution functions, they go uniformly in the variable little t, so from the empirical one to the limit one. And that is due to the fact, as I mentioned yesterday, that these Gaussian measures, they don't charge the boundary of the balls. Okay, so here, like the sphere is not charged by the Brownian bridge. Okay, but other than that is really the same proof. But it's important to have an efficient estimate here. Okay, questions on that? So that was a little clarification just to show you that in practice, and then this so all what I presented yesterday was joint work with Richard Nicol, and we actually implemented this thing for survival analysis recently also with Stephanie van der Pas. So we used this band, several different priors, like histogram priors or wavelet priors, and we then also implemented like the confidence, these credible bands in survival analysis. You can also do the Cox model, which we did with Boning recently. Okay, so that's a nice application also for practical reasons. Okay, so if there are no questions, I'll move to the testing part. So I'll focus on one problem. Actually, the theory is not very developed, although it's very natural. So you know, when you have a posterior distribution and you have two, say, hypotheses, the null and the alternative, it's very natural just to say, okay, what does the posterior think? I'll just look at, you know, the credibility of H0 and the credibility of H1, and I'll decide based on whether one is larger than the other. Okay, so that's called, you can formulate it also in terms of so-called base factor, but it's exactly this. So to fixate this, I'm going to consider the simplest possible problem, in a sense, still a sequence model, but the testing will be multiple because there are many hypotheses. And what are the hypotheses we're going to test? We're just going to make a sparsity assumption, as mentioned a few lectures back, where we assume that the theta is sparse. Most coordinates are 0, except a certain number Sn of those. And so here we call that, so this is a sparse sequence model. So we take the noise to be IID and 0, 1. We could put a sigma here. We could put also other distributions. I'll come to that a bit later. And this is a sparse. So recall that, so theta will be assumed to be in L0 of Sn, which is a subset of Rn of vectors with at most Sn non-zero coordinates. Okay, so 0 is at most Sn. Okay, so the object here that we are going to consider is a test. So let phi be a procedure. So a test is just a usual procedure, so a measurable function of the observations, but we only want to know if a property is true or false, so we just take it at values, taking values in 0, 1. Okay? So for each coordinate, we are going to reply yes or no. So say 0 if we believe that it's drawn under the null, that the coordinate is 0, and 1 if we believe that there is signal on that coordinate. Okay, so there are two problems as seen from the title. Classification and multiple testing, and it turns out they are, at least for this model, quite intimately linked. So what are those more precisely? So the loss of a procedure phi at the point theta, so what we call LC as classification loss. I always forget in which order, theta phi. Okay, so this is just the classification loss is just a number of errors that you make. So they are errors of two types. Either you are under the null and you declare that you are not, okay? So, or the other type of error is that in fact you have signal, but you declare, you think, your procedure thinks that there is no signal. Okay, so that's the type 1 error, and that's a type 2 error. Okay, and let me just introduce, so there is a bit of terminology, so, but I hope it's kind of intuitive. So that's the number of false positives, called the number of false positives. And this is the number of false negatives. Okay, so number of false negatives. Okay, of phi at point theta. And we define from that just the risk is simply the expectation theta under L of the loss. Okay, so today actually we are going to prove, so most of the results will be of information theoretical flavors. So we are going to try to explore the boundaries of these problems. Surprisingly, although there's been a lot of work in this model, especially from the estimation perspective, also from certain, from the signal detection perspective, which is also a testing problem. From the multiple testing perspective, there was no real formalization of the information theoretic boundary in terms of minimax rates. So we are going to look into that and also refine some existing results on classification. Okay, so what is now the multiple testing loss and risk? So while for the classification it's just a sum of errors, multiple testing traditionally will focus on a quantity called the false discovery rate, which is a proportion, and which we'll define now. So the loss, the multiple testing loss of phi at point theta is the sum of two terms. So the sum of false discoveries, so theta I equals 0, phi I equals 1, okay, from 1 to n, divided by the total number of discoveries. So one, as you can guess, maybe the, here, so phi I depends on x. Huh? So at the denominator now, so this is just the number of times we think we have a signal, so it's called the number of discoveries, but this is a random variable. So there will be, technically ratios of random variables are a bit more complicated to study than just plain something linear like we have here. So that's the first part of the loss. So that's called the false discovery proportion. And so that's just, okay, so let me just write it. So that's number of false discoveries divided by the total number of discoveries. Okay? And then there is a kind of a dual part of the loss, which is not completely symmetric for some reasons which have to do with the fact that you could consider something symmetric, but here it's natural to have this kind of dissymmetry, because if you think about it, the non-zero ones and the zero ones in theta are not completely symmetric. They are more, so it's much sparser, the signal, than the zero part. So here we are going to divide by the number of, so if you think a bit about it, it kind of also makes sense. We are going to divide by the number of non-nulls, okay? Which actually, in a moment, I'll assume that this is equal to Sn. So not considering the possibly smaller, but it's a bit easier also to analyze both things simultaneously to assume that we have exactly Sn non-zeros. Okay, so we divide by the number of non-nulls, and here we put just the number of false negatives. So here I could have written actually, so this is NFP theta phi, and here it's NFN theta phi. Okay, so if I assume that this is Sn, okay, so if here I put equal, this is going to be Sn, so this second part of the risk is really the same up to dividing by Sn, but in the first part it is not, so because of this random term, okay? And I get the multiple testing loss, which is theta phi equals to just the expectation of the multiple testing risk, theta phi, and this is called, so the first term, the expectation of this one, of the first ratio, is called the FDR, the fast discovery rate, and the second one is the false negative rate. Okay, so I define both as, so that the expectation of this is the FDR. Okay, so, and this is a very popular measure. So there is I mentioned already, I think the Benjamini-Hirschberg procedure, which is a very famous procedure that controls the FDR exactly or nearly exactly, very close to a given user-specified level. So people in the in the multiple testing community, they really like to work with this ratio, the FDR. So let's try to also obtain results for this, but it will be technically slightly simpler to work with classification. Okay, so some questions so far on the definitions. So quite a bit of vocabulary for now, but.
Can you repeat, because I think FDR stands for what? False?
So sorry, yeah, I didn't write. So it's the false discovery rate. So here I didn't write it. This is called the false discovery proportion, and rate is just because you take the expectation here. Yeah. And this is the false negative rate. And rate just means that we take expectations. So this is the expectation of this term. Okay? So if you find this, so remember that before working in multiple testing, I always had a hard time to kind of differentiate, FDP, FNP, FDR, FNR. Then there is also the MFDR. There is a whole zoo of different. Like also in Bayesian statistics, we have quite some vocabulary. So if you don't want to think too much about it, you can just think of the classification loss, and for the main ideas I'll present, it will be enough. So. And at the end, I will explain also a little bit more about the links. But for now, you can think about the classification loss side. Okay, so some questions that you may ask from the information theoretic perspective. And I mean, you don't have to be Bayesian, to use Bayesian methods to ask those questions. They're very natural. So. One can guess that there are different situations, okay? So if your signals are all, so say in yellow, I plot the signals, and then you have a lot of background noise, okay? Many coordinates are equal to 0, and some of them, the yellow ones here are non-zero. But if I put them all very close to 0, it seems that this problem should be hard or impossible, right? And that's the case. So, but then the question is maybe when does this problem becomes possible? Okay, so there is another situation which is kind of the opposite, which is like the advantageous situation where suppose you have all signals very big and and here you have many zeros. So here it should be possible to detect the signals and to separate well from the noise. And then, of course, the natural question is to understand when is kind of the phase transition between impossibility and possibility, and can we describe this phase transition? Okay, so one first question that you can ask is, if all the signals here are at a certain level A, what should be the A? So if I slide here this kind of line of non-zeros, so only a few of them, because Sn of them are non-zero. If I slide this, at which level does the problem become possible and impossible? Okay, so that's a natural question, and then we can move. So first question. So if all non-zeros, non-zero theta I are at take value little a, okay, we want to characterize like the phase transition in A from possibility to impossibility, okay. That's for question. So the second question is now, of course, this is a nice kind of mathematical problem, but in practice there is no reason why these coordinates are all the same. So now suppose I have completely arbitrary signals. Okay, the signals when I say signal, I mean the non-zero ones. Okay. Here I just, for convenience, I draw them positive, but you could put them on the other side. So what happens for arbitrary signals? Okay, can we characterize the testing, the multiple testing, or the classification difficulty for arbitrary signals? Another question you may ask is, so there are two parts in the risk, okay? So this is kind of like type 1, the FDR, and this is type 2, and the same for classification. So are type 1 and type 2 symmetric in some sense? So do they have the same type of role or difficulty? And another question you may ask is, so in the regime, so one may guess that if A is very big, then there is a regime where the problem is easy, so where the risks go to zero. So if this is the case, you may want to, so called the large signal regime, you may want to characterize the speed, the rate at which this risk or this risk go to zero. Okay. What is the, so this one you have to normalize it by Sn, okay, because it will normalize a bit like Sn, so you have to renormalize it so that this makes sense. But the question is also what are the rates? What is the rate, say, of convergence to zero of, say, of or of LC, of RC, the classification risk divided by Sn, okay, for large signals. Okay, the problem should be, this should be like the easy problem because the risk will go to zero. Okay, so see that there are some subtleties here as well, but okay, so let's try to take the problems one by one. And so questions on what we are going to do. So for now, it's that there is no base here. Okay, yes?
Can we think that the false negative rate is always negative?
No. So all these quantities are positive, right? So they're just positive numbers. So it's just a positive quantity. And what I'm just asking is here, whether they are comparable in the difficulty of the problem. Okay. Other questions? Okay, so if not, we can, let me, yes?
So this Sn, this sparsity, is this something which you imagine to be known or something?
No, thanks for the, so, okay, so generally it's not known to the statisticians, but in a moment, a bit later, of course, to analyze this problem, it may be, so a natural first step is just to take an oracle approach. So if an oracle gives me the value of Sn, which procedure would I imagine? So if I know the value of Sn, probably this problem is not too hard, and indeed. But generally I don't know it, so that makes it difficult, and then we need to do what we have called adaptation to Sn. So Sn is, you can view it in nonparametrics. The analog would be a smoothness parameter. Here it's a sparsity parameter, and generally it's unknown. Okay. Generally. Okay, but I'll come to that because I'll give you a procedure. If you give me Sn, I'll give you a procedure that solves at least the first question quite easily. Yes?
So here, right, because our epsilons, they have constant variance of 1, right?
Yes.
So now for theta, do we assume something like, say, that they're either 0 or let's say greater than some constant c, or they can be as close to 0 as?
No, so here they are, in principle, they are arbitrary. But so in order not to go to the second question immediately, the first step will be to say, okay, suppose they all take a same value, but which may depend on n. So it's important that to feel that here, so I think I mentioned that briefly for when I talked about estimation for this problem. Natural procedures for estimation are thresholding procedures here, and the thresholds value, they lie around square root 2 log n maybe, something like this for a reason. I mean, I'll come back to that, but so it's important that we allow this to go to infinity possibly with n. Okay, but to answer the first question, we will just assume that all non-zero values, that they take the same, okay, same value. Okay, so if there are no more questions, let me just go. So now on this board, let be a bit Bayesian. So let me define a simple Bayesian procedure. We have actually already defined it. So recall that, so we can take, so pi prior on theta, and a natural prior here, remember, would be just the spike and slab prior, okay, where we flip a coin and say, so for now I take alpha fixed. Okay, so alpha is just the weight that you put here. And this slab, so that I call the slab. And here, interestingly, so you could take either Laplace will be fine actually, or Cauchy, or actually any like student distribution as well. Okay, so that was a natural prior, okay, because it puts a lot of zeros in expectation. It puts n times 1 minus alpha zeros. Okay, so then if we have such a procedure, so that's a prior. How can we build a testing procedure? So let me define the L value, at coordinate I is the quantity. So remember, before I wrote the posterior mass of h naught. Okay, so h naught, what is here is just we want to test whether theta I is 0 or not. Okay, so let's just do that. So Li of x, define it as the posterior probability that theta I is 0. Okay, given the data. So here, since the prior is independent, actually this only depends on xi. I can put an xi here if I want, but in general it's just defined like this. So I want to test whether this coordinate is 0. I just look at the posterior mass of this event, so it's very natural. And then I have the L value procedure at level t in 0, 1 is just, I just look at this probability and I ask whether it's small or not, okay? Phi Lt of x at coordinate I is just the indicator that Li of x is smaller than t. Okay, so I just look whether this posterior probability is, say, smaller than a half, for instance. I can take t equal to a half to fix IDs. And then, okay, so that looks quite natural. Okay, so if it looks more probable that this is small, then I will just reject the null, and otherwise I accept. Okay, so let me give now a little proposition which from statistics lectures you may recall as something called decision theory, what we call decision theory. So we will, so I think I mentioned that already once. And when you do decision theory, you work really within the Bayesian model. So assuming in a sense that your prior is correct. So there is no frequentist analysis here so far, I mean with the proposition I'm going to write, but it's a motivation and it will tell me, so this proposition will tell me that in a sense the L-value procedure with t equals a half is the optimal procedure from the Bayesian point of view for the classification loss, and the L-value procedure with level t will be essentially will control the FDR at level t. So, little proposition here as follows. So let me define the Bayesian, so classification risk for a prior pi and procedure phi is just the classification risk that I integrate against the prior. Okay, so instead of evaluating this at a given vector theta 0, I take the average against the prior. So this is sometimes called a bit subjective because it will be, it's a measure of risk that depends on the prior, as suggested by the notation. So this is minimal for phi equals to phi, the L-value procedure with t equals a half. Okay, so that's a very classical result. Let's briefly recall it. And if I look at the Bayesian FDR, so the Bayesian FDR is in the same flavor. It's just the integral of the pointwise FDR at theta against the prior. Okay, so which I can denote by FDR b pi phi. And if I look at the procedure, at the L-value procedure at level t, this is smaller than t. Okay, so from the user perspective, if I'm purely Bayesian under my prior risk, I control the FDR at level t, which is often what's a first requirement in general in multiple testing is to try to control the FDR at least at the user specified level. So in a sense, this says that these L-value procedures, they are kind of very natural, in a sense optimal for classification from the Bayesian perspective. Okay, so the proof is as follows. So I can see the classification, the Bayesian classification risk I can view as the expectation. So this is, recall, this is the expectation under theta of the classification loss. So if here I denote by E pi the expectation in the purely Bayesian model, so this means E pi means that theta and x follow the Bayesian model. Follow the Bayesian model, namely that x given theta is p theta and theta is drawn according to pi. Okay, so this is the expectation of, so I have a double expectation, the expectation under the prior of the expectation under theta. Okay, but since this is the expectation in my whole Bayesian model, I can just write it like this. Expectation of L C theta phi, and phi depends on x. Okay, let me recall it here. And now I can just use the chain rule and say that instead of taking the expectation with respect to theta, as is here, I take inside the expectation with respect to x. Okay, so do that. Given x. Okay, and now I've erased the LC loss, but let me recall it quickly. So it's the sum. Indicator theta I equals 0, phi I of x equals 1, and the symmetric one, theta I non-zero, phi I equals 0. Okay, the other loss. And you see that what's nice here is that taking the conditional expectation, those terms are frozen, right? So you just get the expectation of the first indicators. So you get E pi of the sum over I of, so conditional expectation, this is just the posterior probability of theta I equals 0. This is just the L value, okay, Li of x by definition. This doesn't change, phi I of x equals 1 plus, and now I have 1 minus the L value, which is the posterior probability of being non-zero, so it's 1 minus the L value, indicator that phi I of x is equal to 0. Okay? So if I rewrite this in terms of the indicator that phi I is 1, I get, or I can just factor Li, okay? So what I get is that I get E pi. So I just write this indicator as 1 minus the indicator that phi I of x is 1, okay? So I get sum over I of, so I take the minus here, so twice Li of x minus 1, indicator phi I of x is 1, plus a term which is constant, it's a constant that depends on x but not on phi. And recall that I want to minimize in phi, so this term doesn't depend on phi, I can forget it. Okay, and if I want to minimize this with respect to phi, I can just have a look and see that I can just keep the terms of this sum whenever this is negative, okay, because, and I drop the other ones. So this is exactly, in fact, my L-value procedure at level a half. Okay, so let me just write this. So these arguments, they are quite natural, and I mean, they make it very easy by the fact that we condition on x, okay? So what we get here, so this is minimal for phi x. So I keep this term if and only if 2 Li of x minus 1 is negative. Okay, so I just get the L value. So this is right like this. And I get exactly my phi L a half, okay, of x. All right? So that's classical. And the other thing, which is maybe slightly less classical, but which will be proved in a similar way. So if I have here my Bayesian FDR, so let's do the same trick. So the Bayesian FDR is the expectation, the Bayesian expectation in the Bayesian model of so the FDR, recall, is the expectation of the false discovery proportion, which I didn't introduce formally, but it's just this ratio of random variables, okay? False discovery proportion, I'll write it here now, is just the sum theta I equals 0, so the false positives, so here phi I is 1, divided by the total number of discoveries. And I take sup 1. Okay, so let me do the same trick as before. Yes?
Just have a question. When you say it's minimal for the L-value procedure with t equal a half, it's minimal in all the procedure or in all the L-value procedures?
No, in all the procedures. So essentially, I mean, there are a number of possible values for this quantity, and they depend only on whether a given coordinate, the procedure is 0 or 1. Okay? And if you look at the table of all possible values of this sum, at the very bottom one, the most negative one, is the one where I keep only all negative terms, by definition. Okay? So I remove all positive ones. Okay? So any procedure that does that will achieve the minimum value. Okay? So I can take this. Okay?
Sorry.
Yeah.
So this is also completely independent of the assumption of the noise, right? I mean, that we didn't use that.
Absolutely. Exactly. Exactly. So this is actually a very classical decision theory and beautiful decision theory result, which says that if you are willing to work in the purely Bayesian world where the model is actually coming, your theta is coming from your prior, which in practice could be questionable, okay, because two statisticians could come with two different priors. If you are willing to work in this world, there is a very beautiful theory of optimality, and not only for classifications, but for, so if you take, for instance, a quadratic risk, here as estimator you get classically the posterior mean, and if you take L1 type losses, often you get posterior median, so there is a Bayesian solution as optimal estimator. But the problem is that this is, you can view this as subjective because it depends on the prior. So what I try to do is to take this frequentist approach. Later, in a moment, it will come. I will try to, this is just a motivation for introducing this procedure from the Bayesian world. And it turns out that, in fact, these procedures, if you choose them in a correct way, because, we want to be, want to this adaptive to the data, but given that we chose this wisely, even in a data-driven way, we may hope that they are also optimal, and in fact they will be optimal from the frequentist perspective. But this is not trivial. There is no reason why this would be the case in principle. Okay, so let me do here the same trick of chain rule. So chain rule here, it means that I insert a given x instead of the given theta. And you see that what's nice is that given x, it will freeze everything that's here, okay? It freezes all what depends on x. So here I get e pi, and again here I get my L value, okay, divided by the discoveries. So here if I look at this quantity, I just have, here I'm just averaging, LIs of x, and now what is phi? Now my statement is about the procedure phi LT, okay? And what is phi LT? It's the procedure that is 1 if and only if Li is smaller than t. So which means that under these indicators, all those terms are smaller than t. So here I'm just averaging terms which are all smaller than t. So therefore, I must get something smaller than t. Okay?
Sorry, can I ask something?
Yes.
So in the Bayesian way, actually, the problem is purely probabilistic because you just assume a prior distribution
Yes.
and you want to see the evolution. Actually, because there is a lot of uncertainty put there. For example, the loss function. Is there a way of saying that even the loss function, we are certain about the loss function?
Sure. Yes. So you have to, depending on your loss function, the solution is completely different. Maybe completely different.
So to randomize the loss function.
Why not? But then it's maybe not so clear then if you have, maybe you can prove things like this, but then, I would be a bit more careful, but why not? Yeah. But that's not what I do. I take classical loss functions here.
Yes. Okay. For example, if you have the L1 or L2, you just put dependent on a parameter, which actually I'm not sure what is the eventual loss. So actually I'm randomizing the parameter depending to the loss function. And
okay, so why not?
Yes.
Why not? But it makes a different problem. So I'm not sure the solution is going to be the same. But indeed, maybe indeed in some situations it may be natural to do some different losses. Absolutely. Okay, so now that we have seen this, okay, so we are going now, as before in the lectures, to take a frequentist perspective where, so recall the model is very simple, is this one, okay, with sparse theta I. And I'm going to assume that, in fact, the data has been generated from some fixed true vector theta naught, okay, in L0 Sn. And I'm going to want to analyze the behavior of classification or multiple testing procedure in probability under this law, okay? And so to do that, we kind of guess also from what I said already in estimation, I think in the fourth lecture, that here we probably may want to do the prior more flexible, okay? Because otherwise this may depend too much on the value of alpha. So it's natural to define, okay, so we get naturally, we have already seen it, that data-driven procedure. So you could do full base here for, we investigated it for now for empirical base. So what we do is we looked at here at the empirical base version, okay, where recall that then here we saw that the weight of choosing this was doing the marginal maximum likelihood. But in principle, you could also do hierarchical base, and I think you would get similar results, although we didn't investigate that. So by the way, that what I present today is joint work with Kweku Abraham in Cambridge now, and Etienne Roquin in Paris. Okay, so you can look at this, and then naturally you get what I will call phi EB as empirical base L value procedure. Maybe put the L before. X is just, okay, so this indicator that Li, so Li in fact here depends on alpha, right? Also, I can put it here. So here I put alpha hat. Okay, so very natural procedure. I just plug in alpha hat. Okay, and then one can try to ask, okay, to try to answer these questions. Okay, so let me go for the first question. So question 1, we want to, so that was a motivation and for these procedures. And so here, while I'm erasing, actually, you can ask whether actually this phi L procedure is controlling really close to level T or not. Generally, actually, it's a bit conservative in the sense that it, for the FDR, it controls it. Generally, the Bayesian risk goes to 0. But you can find ways, there are ways to, by taking kind of cumulative L values to make it go, if you want, very close to T. That's also possible. Okay, so now we are going to look at the case of separated signals. So let me define a class of separated signals like this. So the set of thetas in L0 Sn such that if I have a non-zero value, then it's larger than. So here, let me already put the answer here. And I'll try to give you an intuition for this. So for all I in the support, so S theta is the support of theta. So for all non-zero thetas, if I have a signal, I want to be it to be larger than this. And I will also assume that the support, just to identify the cardinality of the support, that it's the support is a size Sn. Okay, so why this log? Well, for now, let's ignore the Sn. So square root 2 log n should be very natural. And why is because the maximum of n01 Gaussians or n minus Sn n01s is actually of the order square root 2 log n. Okay, so I don't know, it's somewhere here. There will be square root 2 log n is kind of natural for this problem. And you see that here you have to slightly change the constant, so if Sn you imagine that is square root of n, for instance, the constant which change slightly in corresponds to the how many non-zero you have, because you want also to detect possibly non-zeros, okay? So you want to be a little bit less conservative than square root 2 log n. And here I have a b, and the b will capture the phase transition from impossibility to possibility, as seen in the next theorem. So let b belongs to minus, so I allow minus infinity or plus infinity in the sense that I can take a sequence bn going to plus or minus infinity. Okay, so I'm in the asymptotic regime where all these quantities, I assume that, so Sn will be a small o of n, but I still assume Sn goes to infinity. And then I have that rho b, the minimax risk, so this is a minimax result, inf over all procedure phis of theta in my class of separated signals of the multiple testing risk is equal to phi bar of b plus little o of 1. So what is phi bar of b? Capital phi is just the primitive of the, so the distribution function of the Gaussian, standard Gaussian, and phi bar is just 1 minus phi, 1 minus phi. Okay, 1 minus phi. All right. So, and you have the same for the classification loss as soon as you renormalize it by Sn. Okay, so what does it mean? Sorry, the classification risk. So here we see the phase transition happening. So if b goes to minus infinity, equal bn goes to minus infinity, rho b is going to 1, which means that the problem is you cannot do better than the trivial procedure that is always 0, which has a multiple testing equal to 1. And okay, so that's impossibility. If b is a fixed real, it's partly possible. Okay, so we go to phi bar of b, so partly possible. And if b goes to plus infinity, then the problem is goes to 0, and it's solvable with multiple testing risk going to, or normalized classification risk going to 0. Okay, and then in this regime, you may ask what is the best possible rate. That's another question. And here, so see that in this type of result we get, so that's what's sometimes called the sharp minimax constant. So you don't only get the transition, but also the best possible constant, a bit in the spirit of the work by Uri Inkster, who initiated the nonparametric testing rate theory in the minimax from the minimax approach. Okay, so here I'm going to go back to Felix's question about Sn. So if you give me Sn, here, given this kind of threshold, which depends on Sn, it seems natural to introduce the procedure that thresholds that keeps the signal if and only if you are larger than square root 2 log n over Sn. And here I ignore the b, but this procedure will automatically adapt to this optimal constant just because it's at the right scale, essentially. Okay, so this procedure, it's not too difficult to see that it achieves, so when we get a minimax result like this, so this is equal up to a little o of 1. In fact, so you have two sides, you have the upper bound and the lower bound. So the upper bound is so achieves the bound. So it gives you the upper bound, and then so it's not too much work. But then the slightly harder part here is to show the lower bound. Okay. So in fact, it's harder for the multiple testing risk because we have this ratio of random variables. For the classification risk is slightly more standard, but still there is a bit of work, and I hope to give you some ideas of the proof a bit later on. Give almost the full proof. Let's see. So so that would be theorem 1, 7.1. Theorem 2. The phi L empirical base. So this is a frequentist result, okay? Because you have a soup here. So if you give me a theta 0 that you don't know in this set, its risk, the risk and uniformly over this class of separated vector is controlled by this. So this is frequentist, but this Bayesian method achieves the bound, achieves the optimal constant. The bound without adaptively, okay? So without knowledge of Sn. Okay, so that's nice. So then you have to work more to show that, but and we do that in a sense by hand, and it would be desirable to actually have generic type results like I presented for rates of convergence, showing that like having a generic testing theory, but unfortunately there is quite very little on testing yet, so we don't have such a theory. So for now we actually rely on really working on the procedures themselves instead of relying on more qualitative arguments. Okay, so that's nice. And so it doesn't use Sn. There are other procedures, like you have some versions of the Benjamini-Hochberg procedure that achieve this, but you have to need a bit more tuning and slightly more stringent assumptions, but not much more. Here there is no assumption extra, so it's really in this setting. Okay, questions before I move to the other questions? So
your procedure is adaptive to Sn?
Yes.
There's no discrepancy between the testing risk and the FGR risk?
Good point. Good. Yeah. Good point. That's not. In principle, it looks a bit weird. You would think that they may be different because this ratio of expectation. So that's a very good question, and it's related to this. And I'll come back to that in a moment of why. But thanks. Yes. Yeah.
So you mentioned some other non-Bayesian procedures that.
Yes.
Achieve the same result, and you said that they have to make more assumptions.
There are probably other procedures, you know. So in fact, the Benjamini-Hochberg procedure is not completely non-Bayesian because you can see that as an empirical-based procedure as well. So here was just when I said extra assumptions, I was mentioning the Benjamini-Hochberg procedure itself. Okay, but in principle, you could maybe find other procedures. I'm not saying this is the only procedure in general. There is no unicity of such procedures. But okay, so let's move to the second question. So here it's a little bit. So you know, it's nice to understand this phase transition, but in practice there is no reason why all the signals would be at a given level or above a given level, and in practice, in general, you have a situation like this with part of the signal maybe very close to zero, and maybe you have to abandon the hope of if it's too close to zero to redetect it, and then part of the signal which maybe is close to these boundaries and part which is large, which is then should be easier to get. Okay, so
sorry.
Yes.
Actually, I think you haven't mentioned yet, in all these procedures, because Bayesians put flat priors many times or improper priors in general, all these results are valid even as long as you have a valid posterior
Okay, so here my prior is proper. It's not, so you could ask the question whether this would also work if I put an improper gamma here, but I don't know the answer. You have to check. I don't know. So what I said is that before in the first lectures that it could help to have heavy tails, so going a bit in the direction of the improper prior, but here it's enough. Even Laplace works. So yeah, there are many priors you could consider in principle, but those are sufficient for our needs here. So arbitrary signals. So you can, I'll just write a class theta b. So it will be in the spirit of minimax local result. So this is in a sense a minimax global result because, I mean, here you allow signals to be larger than this. So some signal, so you could have also some signals here, but maybe you can do better than, and actually it turns out that the lower bound here is reached really for the signals that are around here. And now we are going to make it, the bound also adaptive to possibly different values. So the risk is going to be given here. B will be a vector of coordinates, of Sn coordinates. So the way the class is written is have distinct indices such that theta ij. So here I'm just rewriting the problem, but actually since I will allow for arbitrary bj's here, as long as the quantity I'm writing now is strictly positive. Okay, so bj can be minus square root 2 log n over Sn plus 1, for instance, so that I have 1 here, so that's allowed. Okay, so here I'm just saying that I'm parametrizing my non-zero signals around this threshold, optimal threshold values, and I take just arbitrary bj's around it as long as I get some positive value here. And then what happens is that the previous results hold with optimal constants replaced by some very natural quantity, which is just the average over the signals of the phi bar of bj's. Okay. So with constant, with phi bar of b replaced by 1 over Sn, some j equals 1 to Sn of phi bar of bj. Okay, so that's nice, and in particular what's good is that it gives you a necessary and sufficient condition to be testable. I don't know if it's written this way, but hopefully it's understandable. Testable at level, say, alpha. And this is just taking this quantity and saying so that the lim sup as n goes to infinity of, say, let me call it, is replaced, and here I have to add a little O form. So this I can call maybe lambda n of b. So if the lim sup of lambda n of b is at most alpha. Okay, so when I say testable here is for the empty risk, okay, the multiple testing risk, or that it's classifiable with the renormalization by Sn, Rc divided by Sn. Okay. Okay, so that's nice because you really have, so if I express this, actually, let me rewrite this, but in terms of the theta, it gives you for an arbitrary signal, you can just look at this quantity and see what happens. Okay, so here it will be absolute value of theta j minus square root 2 log n over Sn. And this has to be smaller than alpha. Okay, so for a given signal, completely arbitrary, you may just compute this quantity. So let me give just a little picture. So if you have some signals like this, okay, and here is the oracle threshold, the quantity that you will get here is just the fraction of signals that are above the multiple, above the oracle threshold. Okay, so it's just quite natural. But what's nice is that it's completely minimax local, so it means that you can characterize the difficulty of the problem for any values of signals, not only in this rougher class here, which just allows for larger signals. And in particular, the bounds there, they are of course, so you may apply this for, so if you have a signal, I don't know, a signal like this now, okay, so you may apply the first bound with b equal to the minimal value here, say b minus, but then you'll get phi bar b minus instead of a quantity here, which is better because it takes into account that you have larger signals here. Okay, so that was just to give a bit more intuition. And now let me go to the third question, unless they are more questions. The third question now is, and it's trying to answer Eddie's question. It's a bit maybe surprising that you get the same result for multiple testing risk and classification risk. And why is it a bit surprising? Because in the multiple testing risk, the first ratio, you have on the numerator the first part of the classification loss, but it's divided by the total number of discoveries. So the total number of discoveries can be of order constant Sn, or it's random. So there is a priori no reason why, maybe the boundary is the same, but the constants in principle should change. And the reason why they don't change is that in fact there is a dissymmetry here. And the second type error is, in a sense, is dominating. And since in the multiple testing risk, the second error is exactly the second type of classification error divided by Sn, that's why we get this result. Okay? So let me go to that. So I will need a little definition. So phi, we say that it's sparsity preserving with up to factor an, sparsity preserving, if what? If so I want uniform results. So here I put only this type of, so I will state the result for the easier class, but it works just as well for the more complicated class. And you could even put L0 Sn here, because the condition I'm going to write is actually quite mild and satisfied for most procedures. But I will need it to claim that the second part is dominating, because you always have, like, they cannot be completely dissymmetric, because there are procedures for which the second type error is 0. If you just take the procedure that always replies 1, the second error of the second type is always 0. Okay? So I cannot claim that the second order term in the risk is always dominating. There are procedures for which it's 0. But for natural procedures, namely those that are sparsity preserving, it will not be the case. And what does sparsity preserving mean? It means that this goes to 0 as n goes to infinity, and this is just saying that the total number of discoveries does not exceed much Sn up to a factor an, which we are going to take slowly increasing. So you should think of this as a slowly increasing factor with n. Okay, as n goes to infinity, it can go to infinity. And most procedures you encounter in practice of sparsity model in the literature, but also in practice, like the lasso will satisfy this with actually an typically just a constant, okay? And over all L0 Sn. Okay, so that's a very kind of a mild, but it's a type of, it's a sort of type 1 error control. Because in particular, the procedure that always gives 1 as an answer doesn't satisfy this, because here you get n, okay? So here you can slowly, like an exponential of square root log, something like this. So you can see it as a weak form of type 1 error control. Okay, and there was a question? No, okay. So no trade-off. So suppose an doesn't grow too fast, so we need log an smaller than log n over Sn to the power 1/4. Okay, then for any b in R, so recall I work with a simple class, but I told you it's the same for the more general class, for the arbitrary signals. So here I will not write it, but Can is just the class of sparsity preserving procedures up to a factor an. So if I take the inf over these procedures, sup over theta in L0 SNB of only the second type error, so I don't put the FDR here. So this is phi bar of B plus little o of 1. So what this says is that provided you have this form of weak type 1 error control, it is only the second type error that is driving this constant. Okay. So that was unexpected at first, but if you look at the optimal procedure, actually you'll see, for instance, it's a little calculation, you'll see that the FDR goes to 0 and the FNR goes to phi bar of B. So it already indicates that for the oracle procedure you have this, and of course you can easily check it's also sparsity preserving. And actually for any procedure, as long as it's sparsity preserving. Okay, so that has kind of important consequences. Also, this shows that for the classification risk, the Benjamini-Hochberg procedure controlling at level alpha is always suboptimal. And the reason is because it controls the FDR at level alpha. So the best it can do, since it must pay an FNR phi bar of B, you must pay alpha plus phi bar of B. So you are above, if alpha is strictly positive, you are above this. So then you can say, okay, maybe if alpha goes to 0 in the BH procedure, that can make it work also to have this result, but you have to do something. If you take the standard one, it doesn't work. Okay, so now let me see. So I still want to, so what I wanted to do is to give still maybe a quick answer to question 4 and then give you the proof of theorem 1. So let's see what we can do. And the reason also, another reason why I wanted to show you the proof is that in a sense it's Bayesian, is very Bayesian in spirit. And often to get minimax lower bounds, so there are many techniques. But one technique that is quite helpful, in particular if you want to get the optimal constants, is just to bound the minimax risk by a Bayesian risk. And that is quite powerful generally. But you need to be able to do computations with the priors. Okay, so let me do briefly the large signals case. So here I'll need a lot of structure. So what we wanted to do for this problem was to get an answer without much structure. So assuming really arbitrary, taking really no assumption on the non-zero signals. But if you want to go to large signals, you make already a strong assumption, which is all signals have to be above this value and have to say I have to have this B that goes to infinity, so it's sort of the easy case. So you put a lot of structure, but that's an interesting problem as well. but maybe a bit further away from the philosophy of what we wanted to do first. But okay, so let's look at this problem. So we'll assume that Sn is actually the sparsity is polynomial and bounded below and above by, say, it's of the order of a power of n. Okay, so beta quantifies how much sparse you are, so the larger the sparser. So it's the union of set of thetas which are of cardinality, so support of size Sn, and all the signals are above a certain m_r. Okay, so what is m_r? So for all I in the support. And what is m_r? It's from what precedes, you may guess that you need to have something that's above this threshold, okay, which is the Oracle threshold. And we know from the results I presented today that if you want the problem to be easy, in a sense, you need to let b go to infinity. So you need to be above this threshold. So we are going to take a signal of the form 2r log n with r larger than beta, okay, corresponding to the fact that we want, so beta would be, it's exactly, with my notation, this threshold, okay, because now Sn is of the order n to the 1 minus beta, okay. So I mean this regime, which be like the case of large signals, okay. So now I need a definition. Define kappa. So there are two parameters to which you would like to adapt. There is a sparsity parameter and the signal strength. Okay. So define a certain constant which is square root r minus beta over square root r divided by 2. Okay, that's just the definition. And the theorem is as follows. So the theorem says that the minimax rate for this class, set for the multiple testing risk, is of the order up to constant. So here we don't look at optimal constant. Kappa, the power in the n is the kappa I just defined. Okay, and if you want the classification risk, then you divide by Sn or you multiply by Sn on the right hand side. So Sn times this. So here it's not that surprising that they are of the same order because it's up to constant. So I don't claim that there is a no trade-off result or something like this here, in this situation. In fact, there isn't, I think. Okay. And here you see in particular that if this becomes negative, it will mean that the number of errors on average is smaller than 1. So in fact, you can hope to make no errors at all in the recovery of the support. Okay, so that gives an information theoretic answer to this question of large signals. This is a purely minimax result, but it doesn't tell you that nothing about adaptive procedures. Okay, and now a final result is that, maybe a bit surprisingly, so I could add it here. In fact, adaptation is impossible. Adaptation to both beta and r in the whole range is impossible. And that's quite interesting, because although you may think it's an easy problem because it's large signal, you have two parameters to which to adapt. And the problem is hard in the sense that the rates are very fast. So you want to be very good, and you have two parameters to adapt to, and it's too much to ask. So you can prove that for certain regions of this parameter space, you have a logarithmic loss. A polynomial loss. So the loss in adaptation is not only logarithmic, as we see sometimes in estimation, is really polynomial. So it's really hard to be too good. So that's kind of the intuition you can have for this. So I don't have time to get into the details, and let me maybe take some questions and then start or give you the idea of the proof. Yes?
Is this equivalent
You could see it like this, I guess, yes. So I guess indeed you could view it. So if you put a variance in the noise, you just shift the problem. But maybe it's a bit unnatural to have a variance that goes to 0 or infinity, or maybe there are some problems where there is, or you would want then just to renormalize to be in one or the other situation. Maybe a situation which is also interesting regarding to that question is the case where you don't know the level of the noise, where sigma is unknown. That would make things even more complicated. But so that we just wanted to have a picture really of what's the solution of this problem, which is simple, but there are some interesting phenomena that we didn't expect this, for instance, nor this to arise in this setting. Okay. So if there are no other questions, let me go to the proof of the first theorem. And it's in a sense, I wanted to show you some, it's in a sense, this is well known, when you do minimax lower bounds, that there is always the option to, I mean, many lower bounds proof just start as follows. So you want to control the infimum of the maximum risk. So you have a soup over a certain class. So theta here it will just be shorthand notation for our class. So I'll do the proof is essentially, it's more involved, but it works a bit similarly for the arbitrary signals. You have to work more, but let me do that for the easy class. All non-zeros in absolute value larger than this oracle threshold plus b. So let me look, and I'll look at the classification risk. Okay, so the multiple testing risk is a bit harder. In fact, you have to try to go to a weighted classification loss first, and then argue a bit like for the classification loss, but for the weighted one. And the reason why you can do that is actually precisely because you will weight the first part, the one which you know from the a posteriori, from the further results, that is doesn't count too much. Okay, this is, so you want to control this, okay? So the inf over all procedures, so even before putting the inf, you can just say that this is lower bounded, so the soup is always larger than the integral. So you can bound this from below by the Bayesian risk for any prior, so for pi, a prior on theta. So here you have to be a bit careful because you need the prior to sit on this set. Okay, so you are not allowed to take an arbitrary prior, or otherwise you have to kind of compensate for it. But here we can just build it like this. So this, recall that it is the Bayesian risk, so I may write it this way. Okay, so it's the inf. Now I can take the inf over phi. All right, but if now this may look familiar again, okay, because I'm looking at the best procedure for the classification loss, but the answer, it was somewhere on the board at some time, it is just, you can take the L value procedure, okay? So this is, I know that, so since this is the Bayesian risk for the classification loss, I know that this is in fact attained for the, so this is by the proposition, this is also the Bayesian risk for the classification loss of the L value procedure at level a half. Okay, and this I'm going to bound a bit crudely, but a posteriori again it may not be that surprising. I'm just going to take the second part of the loss. I drop the first part of the loss, okay, which I know actually that it will eventually, you can show that it is not important in general. I mean, it is negligible in general. Okay. Okay. So I take here. I just denote by phi L without the half for just for simplicity. And so here I just take. So this is the type 2 error. Okay. So the error on the non-zero ones, and I drop the number of false positives. Okay. So I can, since the errors are positive, I can do that. Okay, so this I can rewrite as by linearity, this is just the probability under the Bayesian model that theta I is non-zero and that Li, so this is non-zero if and only if phi is 0, and phi 0 means that I am larger than a half by definition. Okay, and I'll denote this by M1. So if you look at the paper, there is an M rho which corresponds to the weighted one, and so if you want some weights, you have to adapt here as well, but it's not much more difficult. Okay, and so let me just give you the idea of the prior. So it's kind of expected here for the classification loss, because you can, for proving the optimal rate of estimation, I mentioned is 2Sn log n over Sn, and to prove that, up to a little o of 1, and to prove that you can use this same prior. Okay, so here, I mean, the fact that it works for classification loss is in a sense well expected. What's also much more work is doing the multiple testing loss. But here, just to give you the idea, is but actually our result is also original for the classification loss, because so it wasn't known, the sharp constant wasn't determined yet to our knowledge. Okay, so choice of pi. Okay, so the idea is that I'm going to split the original problem into Sn sub-problems, and I'm going to argue that I need to study only one sub-problem and then add up the different sub-problems. So I'm just splitting so here I have the integers, 1, 2, etc. Q, so I'll assume, just for simplicity, that n over Sn is an integer. Okay, so if that's not the case, you adapt a little bit, you put zeros at the end, nothing really changes significantly, so you assume that it's an integer. Okay, so if I 2q, and here I have n. Okay, and so I have blocks here, so q1, q2, etc., qsn. I have Sn blocks, and the prior is simply, so for each block qj, I draw an integer ij uniformly in 1q, okay? And I decide that this coordinate is going to be non-zero, and I set the other ones to 0. So here I put the oracle threshold plus b, okay, and that's if my index happen to be equal to ij, and 0 if I is not equal to ij. So I have zeros except at one random place, which is uniform, okay, and I do that independently on each block. Okay, so by construction, this prior is a prior on L0 SNB, okay, this set of signals larger than the oracle plus b, at least this, because I have Sn on zeros and exactly this value, so I'm kind of at the boundary. Okay, and we just now have to bound M1 from below, so I'll just give the ID. So little calculation where you use, of course, now we are going to use Bayes formula to compute the L value. And here, of course, we also use the fact that in this model we can compute. We can also do the proof, by the way, if the noise is not Gaussian. If the noise is subotant, so another interesting name so subotant just mean exponential minus constant x to the q to the say b, well, not b, another letter d. And we only need that d is strictly larger than 1. So Laplace is not included. With the Laplace density, you'll have, you could trade off type 1 and type 2 error, interestingly. But below that, with lighter tails, the results are still valid, and you can actually compute these quantities. So let me just give this, and I'll stop there. So Li of x. So what you need to do, so M1 is defined from the L value, and you just need to compute the L value. So the L value is this. Okay, so by Bayes formula, now you work okay in the Bayesian model. So it's the same. It's another notation for the same quantity. Is this with our prior pi, and this from Bayes formula. So I can say that this is 1 minus. So this is a 1 minus the probability that it's non-zero. But if it's non-zero on coordinate I, it must be that I is equal to ij, right? Just by definition that my prior draws a non-zero only at ij. So that's for I in block qj. Okay? And let me just write the posterior probability, which is here. So by Bayes formula, this can be written as okay, so let's write Bayes formula, the probability of this and this divided by the probability of x. So what's the probability of this? It's 1 over q because it's uniform. And then the probability of x given that I have this is just, so I take the product over k in qj and k different from I of phi of xk, sorry. And then times, and if I'm on the selected index here, I have to shift. So this I will call my signal here that I put, I'll call alpha, sorry, A. So it's shifted by A. Phi A is just the shifted density by A of xi. Okay? And the same at the denominator, it is a sum over all I in block qj. Okay? And so there is a little formula which just, so if you divide by the products of all phi's, and the 1 over q also drops. So you get actually phi a divided by phi. No, sorry, yes, phi a divided by phi of xi and sum over k, all the k's in the block j of phi a over phi xk. Okay, and from there you can, maybe I'll say a word tomorrow about it, you can just write this down and come down to the problem, the difficulty of the problem just on one block, and that you will solve with the phi bar of b. Okay, so thank you very much.